Morning class we started carbocation stability, right? Tell me, what is a carbocation? The organic compound in which carbon carry positive and having how many valence electron? 6 after sharing, called carbocations. Then the stability of carbocation directly proportional to electron releasing group, inversely proportional to electron withdrawing group. So what are the electron releasing group? Plus I, plus M, hyperconjugation. 3 are electron releasing group. What are electron withdrawing group? Minus I, minus M. Only these 2 are electron withdrawing group. Okay. So I think all completed, right? So what are the factors affecting on stability of carbocation? 1. Inductive effect over 2. Resonance effect over 3. Mesomeric effect over 4. Hyperconjugation also completed, right? So hyperconjugation also over, right? Right. Next is rearrangement started, right? Let us continue the rearrangement of carbocation, right? There also one example is completed. Rearrangement of carbocation. Tell me. So let us continue the topic. Second example, example 2. CH3, CH3. Let us take, it is a bromoalkane, reacts with aqueous NaOH. Tell me, what product can be expected? Generally, this Br should be replaced by OH. Br is a internal nucleophile, OH is a external nucleophile. Okay, but product is not that. So then what is the product? Tertiary butyl alcohol is the product. And why this is the product? That is, you need to understand mechanism. Mechanism. In the mechanism, it is a bromoalkane. In first step, it undergo heterolytic cleavage. If it is undergo heterolytic cleavage, Br is minus, CH2 is a positive. Then which carbocation will be formed? Primary carbocation, right? This is a 1 degree carbocation because positive charge present on primary carbon, right? Now tell me, you see the adjacent carbon. On adjacent carbon there is a hydrogen and methyl. Suppose if hydrogen shifted here, what do you get? No. Hydrogen completely shifted here, you will get here positive charge. Which carbocation? Tertiary carbocation. Second case, if methyl shifted here, so which carbocation formed? Secondary carbocation, right? That means if hydride is shifted, you will get tertiary carbocation. If the methyl group is shifted, secondary carbocation, then which is most stable? Tertiary. Therefore hydrogen shifted. So that is, which is called 1,2 H minus shift, hydride shift. So therefore tertiary carbocation is the intermediate. Okay. Now this tertiary carbocation reacts with OH minus nucleophile because we have taken aqueous NaOH, right? Here we should take aqueous NaOH. So therefore now OH minus attack on carbocation to form the tertiary butyl alcohol is the product. This is how rearrangement takes place. Okay, that means the rearrangement takes place by what? The shifting of hydride. Okay, is it only shifting of hydride? There may be a shifting of hydride, there may be a shifting of alkyl group, even shifting of aryl group also. Therefore, therefore we have types of shift. What are the types of shift? Tell me. No, this reaction do not take place single step. This is one step, it is another step. 2 step I have written in single equation. So this reaction takes place in 2 steps. Okay. Next, types of shift. 1. It is a 1,2 H minus shift, which is called all right, clearly 1 comma 2 hydride shift. Okay, 1 comma 2 H minus shift. Second one, 1 comma 2 alkyl shift. Which is also called 1 comma 2 R minus shift. Third one, 1 comma 2 phenyl shift, or aryl, of course aryl also, phenyl or phenyl derivative aryl. It is a 1 comma 2 pH minus shift. So therefore there are 3 types of shift. One is a hydride, 2 alkyl, 3 phenyl shift. Okay, then now let us see one example. This is a carbon having methyl group and a hydrogen, and here is phenyl, and this is a carbocation. Okay, of course it is a primary carbocation. Okay, so primary carbocation unstable. If it is converts into secondary, tertiary, it become more and more stable, or allylic or even benzylic, it is more stable. Therefore now we need to see the possibility. Adjacent to carbocation there is a hydrogen, there is a methyl, there is a phenyl. Now which has to be shift? So that is called migratory aptitude. So what is the migratory aptitude of these 3 groups? So remember, among the 3, hydride is, now the shifting of hydride takes place very fastly, very quickly, or very easily. That means if you see the migratory aptitude, hydride is very, very fast due to its small size. Okay, next, but actually the migratory aptitude depends on the electron density. So therefore migratory aptitude is directly proportional to electron density. Higher the electron density, more will be the migratory aptitude. So therefore now tell me, among these 3, hydride will shift easily. See, it is, we are calling it is a hydride. Which hydride it is a 1 comma 2 H minus shift. H minus. Okay, so H minus in the sense this H come along with bond. Without bond H plus, with bond H minus. Okay, therefore then what is the intermediate? This methyl group will be same, positive charge comes here, this is a phenyl, and this is H2, CH2 become CH3. This carbocation is a, it is a tertiary, carbon, no, it is a phenyl, nothing but benzene ring, phenyl ring, right? And it is a tertiary, and most important it is a benzylic carbocation, right? This is also called what? Benzylic carbocation. So which is more stable. Then is it undergo further any rearrangement? No. You see adjacent, it is a methyl, primary. Here no hydrogen, it is not possible. That means this itself is a most stable. Okay, then next break this point, migratory aptitude. Migratory aptitude is directly proportional to usually electron density. Migratory aptitude directly proportional to electron density. Okay, can you tell me, it is except hydrogen. Even though hydrogen has only 2 electron, H minus, no, 2 electron, but hydrogen migratory aptitude is highest. Why? Because of small size. So therefore what is the migratory aptitude of these 3? Remember, H minus has highest migratory aptitude. It means H minus can migrate very fastly. among the given group. Then next is, can you tell me which one has highest electron density? Hydrogen, methyl or phenyl? You leave the hydrogen, phenyl, because phenyl ring has 3 pi bond, it means 6 pi electrons. So that's what benzene ring is called, electron rich. Benzene ring is electron rich because of 3 pi bonds. Therefore phenyl ring pH minus has more migratory aptitude. Then next is alkyl. In alkyl, if you take different groups, tertiary, tertiary alkyl is more. Next is secondary alkyl group. Next is primary alkyl group, and next is methyl group. Okay, these are all are negative charge. This is the migratory aptitude of the different groups. ಅಲ್ಲಿ ಸರ್ ಬಂದರೆ 7:30 ಆಗ್ತದೆ ಕ್ಲಾಸ್ ಅಂತ ಹೇಳಿ. ಟಿಲ್ ದಟ್ 7:30 ಕ್ಲಾಸ್ ವಿಲ್ ಗೋಯಿಂಗ್ ಟು ಫಿನಿಶ್. Okay. Right? Now let's see some important examples. Okay, let us take methyl group, ethyl group, phenyl group, CH2. You just write the rearranged carbocation. Write the products. Okay, tell me. So with respect to this carbocation, it is a ethyl, phenyl, methyl. So there is a migration of phenyl takes place because phenyl ring has more electron density. Next, with respect to carbocation, tell me, this carbon has one ethyl, methyl, tertiary butyl. So which has migrate? Tertiary can migrate. So migratory aptitude of tertiary is more because of electron density. Next, here all are phenyl ring, 3 are phenyl ring. But phenyl ring attached to electron withdrawing, electron releasing, electron withdrawing group. this is electron releasing group, this is electron releasing group. Both are electron releasing group, means electron density is more. Among two electron releasing group, which has more electron density? So either methoxy or methyl. Methoxy, because it is a plus M effect, this is a plus I effect. So plus M effect dominates plus I effect. Yes or no? This is a plus M group, it is a plus I group. Therefore, now this is migrate. Right? So this is the migration of different groups. Okay, will you write? Next is some specially stable carbocations. Some specially stable carbocations. Right, some specially stable carbocations. There are two important carbocations very stable. One, aromatic carbocations. This is we have studied. I will write some example. Aromatic carbocations. So wherever aromatic carbocation comes, which is most stable because of aromaticity. Okay, can you tell me example? Which example we have studied? It is a 3 carbon ring having positive charge and 1 double bond, which is called it is cyclopropyl cation, carbocation. Okay, cyclopropyl carbocation, right? Now question is, cyclopropyl carbocation is stable or unstable? It is exceptionally most stable. Why? Aromaticity. It is aromatic. So how many pi electron? 2 pi electrons, and cyclic, it having planarity, Huckel rule, obeys Huckel rule. Therefore it is a aromatic, therefore most stable. Right? So wherever aromatic carbocation comes, which is most stable. Next, another example. Let us take cyclobutane, which is having 1 double bond and 2 positive charge. Tell me, what is the name? Cyclobutynyl, butynyl, cyclobutynyl dicarbocation. So therefore cyclobutynyl dicarbocation means 2 positive charge will be there. Come on, tell me, is it stable or unstable? Stable. Why? Aromaticity. So therefore it also 2 pi electron and it is aromatic. But another most important is, there is a 7-membered ring. Yes, 7-membered ring and positive charge will be there, which is called tropylium cation. So remember, among aromatic cation, tropylium cation is most stable. Its name is tropylium, common name. Tropylium carbocation, which is a most stable aromatic carbocation. Okay, so therefore wherever carbocation gets aromaticity, which is most stable, these are the aromatic carbocation, they are especially more stable. Next, there is another carbocation, it is also exceptionally most stable, that is second one, cyclopropyl methyl carbocation, right, which is also called CPM. Here onwards I use this only, CPM, cyclopropyl methyl carbocation. So cyclopropyl methyl carbocation also exceptionally most stable. Then what is the structure of CPM? See, this is a cyclopropyl group, and write one carbon atom which is CH2 and positive charge. This is a CPM, cyclopropyl methyl carbocation. So this carbocation exceptionally most stable compared to any other carbocation. Suppose question is given like this: which of the following is most stable? If the option is there, if there is an option with this, you need not to see any other options, go for CPM. Even this also, tropylium also, right? So CPM is most stable. After CPM, tropylium comes. So therefore CPM is exceptionally most stable carbocation among the given carbocations. Then you may have doubt, what is the reason? So what is the reason for this? Hyperconjugation not. Okay, hyperconjugation is possible, one hydrogen is there, that is possible. But what exact reason? Hyperconjugation means there are many molecules having hyperconjugation, but they are not stable like equally with CPM. But here reason is, do you know in CPM there is a cyclic ring and CH2 which has of course positive charge, and this has one vacant p orbital, we know it. Carbocation has one vacant unhybrid p orbital. So this is a vacant and unhybrid. Vacant unhybrid p orbital. So therefore this vacant unhybrid p orbital which is overlap with the sigma bond of this cyclopropane, this is sigma bond. Now this is overlap with this. How? You can write in another way. I will write in this way, right? It has a sigma bond, this is a sigma bond of cyclopropane, and I will take another carbocation here, it is a CH2. This CH2 has unhybrid vacant p orbital. So now these two have partial overlapping. Due to partial overlapping of these two orbital, it may be stable. That may be, right? So therefore the overlapping between what? Sigma bond of cyclopropane and unhybrid p, vacant unhybrid p orbital of carbocation. So this may be the reason for the extraordinary stability of CPM. Okay, so these two are the especially stable carbocation. Now let us see the overall stability of all carbocation. What is the overall stability? Okay, see, before going overall stability, one example you just take. It is a tertiary CPM. There are 3 CPM. See, 1 CPM is most stable. If there are 3 CPM, it is again extraordinarily stable. Therefore, tertiary CPM most stable compared with 2 degree CPM, which is most stable compared with 1 degree CPM. Yes or no? Next, another example. Suppose if I take triphenyl methyl carbocation, which is most stable, compared with what? Diphenyl methyl, then which is compared with benzyl carbocation. Yes or no? Next, another example. For example, if you take CPM and tropylium, CPM and tropylium, tell me which carbocation is most stable? Obviously CPM is more stable than tropylium. Okay, then tropylium more stable than triphenyl. Then you can understand how tropylium is more stable. Okay, even though there are in triphenyl there are 3 phenyl rings which has 12 RS. Even though there are 12 RS, but tropylium is more stable than triphenyl methyl carbocation. Okay, now tell me, by keeping all these things in mind, can you write the order of stability of carbocation? Order of stability of carbocations. Tell me, if you see the carbocation, which carbocation is most stable? So 3 degree CPM. So therefore, first comes 3 degree CPM is most stable. Then 2 degree CPM. Then CPM. Then tropylium. Yes or no? Tropylium, then triphenyl, then diphenyl, then benzyl. Okay, then after benzyl, which carbocation is most stable? Tertiary or allylic? Allylic, because conjugation resonance. Allylic most stable. Then 3 degree carbocation. Then 2 degree carbocation. Then 1 degree carbocation, primary carbocation. Then methyl carbocation. Then alkene carbocation, then alkyne carbocation. Then last comes phenyl carbocation. It is highly unstable. Right? So this is the order of stability of different carbocations. Okay, say majority question comes based on stability. In all reaction intermediate, 90% questions are based on stability of intermediates. It may be carbocation, carbanion, free radical. There are very few questions based on other concepts other than stability. That's what you focus on: stability. Which is more stable, which is less stable, which of the following has highest stability, least stability. So all questions are like this only. That's what I think this one sequence order enough to understand 90% questions in carbocation. Okay. So it is about stability of carbocations. Next is then rearrangement of carbocation. Now before that you write a question. Write the product in the products in following rearrangement. Write the products in the following rearrangement of carbocation. 1. Okay, so just write the rearrangement products. Tell me. See here, you try to understand first which carbocation it is. 1 degree carbocation, right? Then you see adjacent. Adjacent is there are 2 hydrogen. Suppose if hydride is shifted here, what is the possibility? 2 degree carbocation stable, therefore possible, right? Like that. It is a 1 degree carbocation. Adjacent carbon, there is a methyl, and there is 1 hydrogen. Then tell me, what is the migratory aptitude? Hydride shift is more, therefore shift the hydride, then the product is, so methyl will be same, that is tertiary carbocation. Next, adjacent carbocation, there is a hydrogen, carbon hydrogen has, adjacent carbon has hydrogen, here is there are 3 hydrogen. Tell me, see the 2 sides, if the hydrogen shifted this, you will get which carbocation? Tertiary. If this hydrogen shifted, primary. So therefore tertiary is more stable, that's what this is shifting is possible. Yes or no? Next, so this side is methyl, okay, here is there are only 3 methyl, there is no hydrogen. Okay, now tell me, so here if this hydrogen shifted, you will get a primary carbocation, but already it is a secondary. So secondary may converts into tertiary, it may converts into allylic benzylic, but not primary, because most stable do not convert into less stable, that is not possible. That's what. Now what we have to shift? So we should shift methyl group, shift this methyl group, therefore then what is the product? There will be 2 methyl groups same, and 1 methyl come here, it is positive. Okay, next tell me this is a which carbocation? 2 degree carbocation. What is other possibility? Both the side 2 hydrogens are there, and if hydrogen shifted, again what possibility? Secondary. Therefore secondary equally stable, therefore there will be a shifting. Why? Suppose, see, if this carbocation shifted this side, what do you get? Secondary carbocation only, but this secondary carbocation is more stable, because you see for this there are how many alpha hydrogen? Alpha carbon, so 2 plus 2 4, no, there are 4 alpha hydrogen, it means hyperconjugation, 4 hyperconjugation possible. But here how many alpha hydrogen? CH3, it is CH2, how many? 5 alpha hydrogen, this is more stable, because as the number of alpha hydrogen increases, hyperconjugation increases, stability increases, even though both are secondary, right? Both are 2 degree, but one is more stable because of hyperconjugation. Next, tell me quickly. So here there are 2 hydrogen, here 1 hydrogen, and 2 methyl group. What is the shifting? Hydride, right? Shift this here, therefore the product is tertiary carbocation. Next, now see, adjacent 2 hydrogen, this is 1 hydrogen. If this 1 hydrogen shifted, you will get tertiary. If this 1 hydrogen shifted, secondary. But which is more stable? Tertiary. ಎಷ್ಟು ಈಸಿ ಹೇಳ್ತಿದ್ದೀರಲ್ಲ? ಮತ್ತೇನು ಬರಬೇಕು? Secondary is more stable, because if this hydrogen shifted, you will get of course secondary carbocation. Carbocation will be secondary, but there is a possibility of what? Hyperconjugation. What is it? Plus M effect. So due to plus M effect, these lone pairs form the pi bond, right? It means plus M effect is most important for stability of carbocation. One point you have written. If there is a plus M effect, you need not to see any other effect. Plus M effect stabilize maximum. Okay, next. It is also same, right? So this is hydrogen, no? Shift hydrogen will get positive charge here because it is also plus M effect possible. Tell me there. So here methyl has along with methyl hydrogen will be there. There are two hydrogen. Tell me which hydrogen will be shifted? Either this methyl or this methyl only. Why? It become tertiary, right? But not. Why not? The reason is, if this hydrogen shifted here, you will get the carbocation here. Let it be this is methyl same. Then this is what? This carbocation is a benzylic carbocation. Benzylic carbon, no? Adjacent to benzene ring, benzylic. Benzylic carbocation has 4 Rs. This is it will get tertiary carbocation. So it do not form tertiary because benzylic is most stable. So wherever stability comes, it goes that side only. Okay, ideri same. So shift hydride here, benzylic carbocation. Tell me this. So there is a one hydrogen, no? Not there. See the valency. So there will be a hydrogen on bridgehead carbon. Tell me now. So yeah, if hydride shifted here, you will get carbocation here. So which carbocation that is? Tertiary. Tertiary is most stable. Okay. Most stable, no? But not. Why? According to Brett's rule, bridgehead carbon never get planarity. It means never get sp2. Actually, it is above the ring like this. If you write sp2, this has to be on plane. It has to come on the plane. That is not possible. That means this conversion not possible. It means it do not convert according to Brett's rule. In the same way, we have studied enolization. Remember? Enolization. Enolization also not possible. It means double bond do not come here. Double bond also equal to carbocation because sp2 sp2. Same concept. So therefore, enolization as well as shifting of bridgehead hydrogen is not possible. Okay, due to non-planarity. It is a non-planar. Next, here also same, right? There is a methyl hydrogen is there. So therefore, you shift here, you will get positive charge. That is possible. Is it possible here? No. Right, next, right? Rearrangement of carbocations. Rearrangement in cyclic carbocation. in cyclic carbocation. Okay, so the rearrangements in cyclic carbocation. Okay, so in cyclic carbocation, in cyclic ring there are two type of rearrangement takes place. One, the rearrangement takes place by expansion of cyclic ring. It is by expansion of cyclic ring, means ring opens and a new ring will formed, that is called expansion. And the rearrangement of carbocation takes place by contraction of cyclic ring. Ring size will be reduced, contraction. Therefore, there are two types of rearrangement in cyclic carbocation. Types of rearrangement: one, ring expansion; two, ring contraction. Tell me, first one, ring expansion. Ring expansion in the sense smaller ring converts into larger ring. Okay, so therefore here we have only two example, that is, first one is A. In ring expansion, 5-membered ring usually converts into 6-membered ring, because 6-membered ring is most stable. We have studied its puckered conformation, that is chair conformation. In chair conformation, it has 6 equatorial, 6 axial hydrogen. Due to equatorial axial hydrogen, 6-membered ring become most stable. That's what C5 converts into C6. This is one possibility. Okay, next is B. Another possibility is there will be a 4-membered ring also converts into 5-membered ring. Compared to 4-membered ring, 5-membered ring is stable. Okay, therefore there are two ring expansion, C5 to C6, C4 to C5, but first one is very important. We have many more example. Next is ring contraction. In ring contraction, larger size ring converts into smaller size. Here we have only one example, that is 4-membered ring converts into 3-membered ring. Can you tell me why? When 4-membered ring converts into 3-membered ring, it forms CPM. CPM is a what? It's not party. Most stable carbocation. Okay, so that's what C4 converts into C3. Now let's study first ring expansion. Ring expansion. In ring expansion, remember 5 to 6, 4 to 5. Okay, let me see first 4 to 5. 5 to 6. Okay, 5 to 6. Let us take 5-membered ring. Okay, and it is a CH2 which has positive charge. Listen carefully. Okay, now I'll take, this is carbon 1, 2, 3, 4, 5. Right, in ring expansion what happened? The bond, like it is a 1 and 5. So this bond shifted here because it's a 5-membered ring. This bond is shifted where? On carbocation. Therefore, first you will get the intermediate structure. If you write intermediate, it becomes easy to understand. That's what. Okay. Then in intermediate, this bond partially broken, and a new bond will be formed. Again, it is partially formed. It is partially broken, partially formed. So again, it is a 1, 2, 3, 4, 5. Okay. Then it becomes 6, no? Okay. Now next step. The bond between 1 and 5 is completely broken. It is completely formed. Okay. Therefore, so you can write another step also. I'll write as it is till here, same, no? Okay, this bond disappear and a new bond is formed permanently like this. Okay, irli adu hange. Now tell me where the bond disappear, on which carbon? First carbon. Therefore, now what about fifth carbon? Fifth carbon bond is losing but new bond forming. Therefore, so fifth carbon, do not bother. It is losing one bond, it getting one bond. But it is a problem for first carbon. First carbon losing bond permanently. So therefore, first carbon gets positive charge. Therefore, this is 1, 2, 3, 4, 5, 6. Then which is equals to this, right? It is called ring expansion. 5-membered ring converts into 6-membered ring. For ring expansion, there is a one important condition where the ring expansion takes place. Ready? For ring expansion, there should be a positive charge, or positive charge should be present outside the ring, not on the ring. Okay, for ring expansion, positive charge should be present outside the ring, that is alpha position with respect to ring. It is a cyclic ring. With respect to cyclic ring, this is the alpha carbon. On alpha carbon, there should be positive charge. If there is a beta gamma carbon, no. Therefore, a positive charge must be present outside of the ring. That must be alpha position with respect to cyclic ring. Therefore, that is a condition. For ring expansion, positive charge must be present on outside of the ring okay, that is alpha position with respect to cyclic ring. So with respect to cyclic ring, it must be alpha, it must be on alpha position, then only ring expansion is possible. Okay, I hope you understood. Now one more example. Let us take similar example. It is a cyclopentane only. Suppose if the positive charge here, is it ring expansion possible? No, never. Positive charge must be where on alpha position. Now it's possible. Okay, then tell me what is the rearrangement of carbocation? It is a 5-membered ring. So therefore, better you give the numbering, it is easy to understand the expansion. Okay, then this 1,5 bond shifted here. Then you will get the partial breaking and partial making of bond. This is a partial breaking, partial making of bond, and numbering will be same 1, 2, 3, 4, 5. It becomes 6. Then the bond between 1,5 is completely broken, and a new bond 5 and 6 is formed. So therefore, I'll write directly cyclohexane the bond. And where the positive charge comes? Either on this carbon, adjacent carbon. Which carbocation it is? Which carbocation it is? Secondary. But there is another possibility. Another possibility is this. There is a hydrogen adjacent carbon, you will get tertiary carbocation. Therefore, another rearrangement possible. So therefore, then finally you will get tertiary carbocation, which is more stable. Okay. So therefore, you may have doubt how far it takes place until it gets stability. Primary to secondary, secondary to tertiary, tertiary to benzylic, allylic, like this. Until gets most stable carbocation, it goes on, rearrangement takes place. You need not to have any restriction to rearrangement. Okay, next one more example. Let us take cyclobutane, okay, which has CH2. Tell me, what is the product, or what is the rearrangement product? Yes or no? Shift the bond. 4-membered become 5-membered. One more. If there is a 4-membered ring, tell me, what do you get? So after ring expansion, you will get, first you will get 5-membered, no? Then where the positive charge? Here, no? Because adjacent, right? Next, another rearrangement. 6-membered, 6 antrala tertiary. For the ring expansion, where the positive charge, it must be outside the ring, not on the ring. It is on the ring. If the the positive charge present on the ring, no ring expansion. Instead of expansion, contraction takes place. That is a condition for ring contraction. Therefore, you will get this. Then one more condition. Suppose ring expansion possible, tertiary has to convert into primary. Is it possible? No. So carbocation doesn't come here. When carbocation doesn't come here, then where is the question of ring expansion? No ring expansion, right? This is ring expansion. Next is ring contraction. Tell me, in ring contraction, there is only one ring contraction which is possible, C4 to C3. Okay, now let us take 4 carbon having cyclobutane, which is having positive charge here. Okay, now tell me, what is the ring contraction? In ring contraction, again you can take numbering here 1, 2, 3, 4 and 3, 4 sigma bond. This sigma bond shifted here. Okay, tell me, when the sigma bond is shifted here, which bond is partially broken? 3 and 4. Okay, the remaining things are same. Which bond is partially formed? 3 and 1. 1, 2, 3, 4. Then finally, this 3 and 4 bond completely broken. It means where the positive charge comes? 4th carbon, right? Here, that's what. This bond will be formed and here is CH2. This is nothing but, it is a CPM, right? So due to formation of CPM, this conversion is possible. But what is the condition for the ring contraction? It is opposite to that. For ring expansion, positive charge must be present outside the ring, that is on alpha position with respect to cyclic ring. But ring contraction, positive charge must be present on the cyclic ring. If not, contraction not possible. Therefore, condition for ring contraction, positive charge must be present on cyclic ring. So on the cyclic ring, positive charge should be there. Then only it is possible. Okay. Some examples, write on question form. Write the products in following rearrangements. 1, 1, 2, 3. Okay, will you do it? You try it.